So, how do you find a flaw hidden deep inside a solid object? I mean, really deep. And maybe even more importantly, how can you actually trust what you see? Well, today we're diving into the world of industrial CT scans and the critical rulebook that makes it all possible. ASME Article 20.
Just think about it for a second. Imagine trying to find a microscopic crack inside a jet engine turbine blade, or making absolutely sure a medical implant is perfectly formed from the inside out. You can't just cut it open to check, right? This is the exact challenge that industrial computed tomography, CT scanning, was built to solve.
You can think of it like a super-powered X-ray. Instead of just one flat image, a CT scanner takes thousands of pictures from every possible angle. Then, it uses some seriously powerful software to stitch all of that together into a complete 3D model. It literally lets us see the invisible without ever leaving a scratch on the part.
Okay, but with that kind of power comes a whole lot of responsibility. How do we know the image we're looking at is actually the truth? How can a manufacturer in one country trust a scan from a supplier halfway across the world? We need a universal standard. We need a rule book everyone agrees on.
And this is exactly where ASME's Article 20 comes into play. It's the definitive guide, the gold standard for industrial CT examination. It provides the framework that turns this amazing technology into a process that's not just powerful, but completely reliable and repeatable.
So how does Article 20 pull this off? Well, it's all built on a very simple but totally non-negotiable principle. Every single scan has to start with a master plan.
And the standard is not shy about this at all. Section T2021.1 puts it right there in black and white. The exam shall be performed according to a written procedure. Notice that word, shall. That's not a suggestion. It is the mandatory first step. No exceptions.
And the level of detail that has to go into this procedure, it's just immense. This is just a partial list of what they call essential variables. Every single detail, from the type of radiation source and its voltage to the specific software algorithm used to build the 3D model, has to be defined and approved before a single scan even starts.
Really, the best way to think about it is like a pilot's pre-flight checklist. You just don't skip steps because you're in a hurry or you think you know better. Under Article 20, the written procedure is absolute. It's all about ensuring perfect consistency every single time.
But, a great plan is totally useless if you don't have the right people and the right equipment to actually make it happen. You can't just have anyone walking up and operating this incredibly sophisticated equipment. Article 20 makes it crystal clear that only qualified personnel can handle any part of the process, from taking the pictures to making sense of the final data.
And these qualifications are seriously strict. Operators have to be certified as what are called Level 2 or Level 3 examiners, and they need fully documented training and proof that they can actually do the work. It is all about having verifiable human expertise at the controls.
Of course, an expert is only as good as their tools, which is why the standard puts just as much focus on making sure the equipment is perfectly calibrated and performing exactly as it should.
Take something called detector pixel correction, for example. Before you can trust any image, you have to know the camera, the detector, is flawless. This means running scans to correct for any background digital noise, and then making sure every single pixel reacts to radiation in the exact same way. It's basically a digital deep clean of the lens to guarantee a perfectly clear picture.
Okay, so we've got the plan, we've got the expert, and we have a perfectly calibrated machine. Now it's time to make sure the image we actually capture meets the highest quality standards.
So how do you prove the whole system is working correctly in that exact moment? Well, you do a quality check using something called a representative quality indicator, or an RQI. This is basically an object with features or flaws that you already know about. If your scan can clearly see all those known details, then you can be pretty darn confident it's going to accurately capture any unknown flaws in the real part.
Now, after the scan, there are two layers of review. First, there's a preliminary evaluation. That's a technical check to look for any image glitches like weird artifacts or bad pixels. But the final call, the verdict on whether the part passes or fails, that belongs to the manufacturer. They are the ones responsible for interpreting the data and officially accepting the component.
And finally, none of this would mean a thing without the last and maybe the most critical piece of the puzzle, the documentation. Every single step has to be recorded.
And I am not kidding when I say every step.
The standard requires this incredibly detailed, exhaustive record of every single parameter that went into the scan. It creates a complete, unbroken paper trail for the entire procedure.
You can kind of group these dozens of requirements into a few key areas. A huge chunk of it is the scan setup and the image data itself. But it also includes things you might not think of, like the specific part number and even the exact versions of the software that were used. It's a complete snapshot of the entire process, frozen in time.
So why do all this? Well, this paper trail creates an unbroken chain of accountability. This isn't just busy work. It's the proof that a critical component was inspected correctly. If there is ever a question, maybe even years down the road, an engineer can go back and verify that the inspection was done perfectly. It is the ultimate guarantee of quality and safety.
So that's the whole journey. ASME Article 20 provides this incredibly rigorous structure that takes an amazing technology and transforms it into a completely trustworthy and verifiable process. It's the system that lets us confidently see the invisible every single time.
It really makes you appreciate the critical and often unseen role that standards play in our world. They are the bedrock of safety and quality for so much of the technology we rely on every single day. And it kind of makes you wonder, doesn't it? When precision is everything, what other invisible details or standards helping us see?